Hello everybody. I would like to welcome you to the ZW 2021 digital session on solving low power DDR4 technology design challenges using the CR-8000 PCB design process. My name is Ralph Bruening. I'm working as a product manager and senior consultant for high-speed design issues for signal and power integrity at the Zuken EMC Technology Center in Paderborn in Germany. And I'm glad that you're interested in listening my session. I've structured the session in a way that I would like to give you a short motivation and explain some backgrounds on the memory evolution from past to present and what's coming in future at the end. I would like to explain a little bit what's the meaning of the fourth generation of low power DDR, DDR4, and what is the impact of narrowing down the voltage levels of these memory devices on a daily basis. Then I would like to pass over to the aspects of implementing low power DDR4. So what's the meaning of the dedicated design constraints of low power DDR memory? How this can be implemented, how this can be validated and analyzed, and what's the meaning of JEDEC compliance, what's the meaning of IC vendor compliance, what is the role of signal integrity and power integrity in that process, and how this is addressed using CR-8000 from front end to back end, from design gateway to design force. And then I would like to close with a summary, with a kind of takeaway for you, and what is the outlook to future memory systems coming rather soon. That's what we have to say. And what's probably pretty important in the beginning, memories and memory devices are everywhere. So memory interfaces are pretty important. We have them on computers, we have them in cameras, in cell phones, in gaming applications, in IoT applications to a certain extent. Sometimes one memory device, sometimes DIMM module, sometimes memory down. And we have them in a growing importance in industry automation applications and in automotive. So if we look into the electronic engineering process, which you have to operate in today, we have the situation that products should be designed in shorter time at lower cost with higher performance. So design right first time is gaining more importance. And not all, but most of our products see the situation that we have an increasing demand for more bandwidth. So we have 3D graphics, even on a coffee machine. We have these days these animations showing you cappuccino coming into existence. We have larger screens, higher resolutions, we have streaming, we have gaming. We have connected devices, we have these connected mobile devices. So battery power, standby time is important. So all these aspects make electronic design more complicated these days. And we have DDR memories everywhere. So you should not be surprised. And the question is, will the system work at all? Will it work at the desired memory grade, at the speed you would like to have it working? And another aspect, and I've seen cases where this was not the situation, will it work in mass production? So not only the prototype defined by a PCB manufacturer somewhere close by, will it work as well from mass production from Asia or from second sources? So what is your tolerance level? How much is the yield? That's where the procurement and the bookkeepers are interested in. So the using of a tool-based process comprising analysis steps, constraining steps, simulation steps, not necessarily that every net should be simulated. That's not what I would like to point to. As well, measurement could be a measure, could be a tool being important in the process. So all this is paramount to ensure a proper device operation. So the question is, in this process, what's better? To work with guessing, to work with estimations, to work with rules of thumb, work as you did work in the past, sprinkle the board with decaps, use the same layer stack you used before, regardless whether it's DDR2, DDR3, whatever, or to use proper analysis steps and simulation and measurement. So what is probably the recommended design process? These questions I like to answer during my presentation. From the technology motivation point of view, so why do we have these fast memories everywhere? There are different driving factors. So there are cloud applications. So we have connected devices which then hook data somewhere into the cloud. We have a lot of data which is collected by all these sensors and actors in IoT devices. We have parallel computing requesting more memory power. Okay, you may state that's not my business. We have as well the situation that we have more memory available in smaller IC form factors. So we have combined dies, and at the end, your electronic engineers designing your products will use all these features which the silicon vendors will provide them. We have an increase in the bandwidths. So we have a higher bandwidth from DDR3 to DDR4 and meanwhile to low power DDR4. And we have this decrease in the power requirement, decrease in the voltage level. DDR3 was 1.5 volt. DDR4 is 1.2 volt. Low power DDR4 is narrowing down even further. So we are at 1.1 volt. There's a low power DDR4X breed, which is operating at half of that voltage levels. And we have the situation that the memories, meanwhile, occupy or consume the majority of the overall system power. So that's a study already 5 years old from Intel, presented at DesignCon, where they have studied where the different power demand is occupied. And meanwhile, half, and I would suspect 5 years later even more, half of the power is consumed by the memory. And that's quite interesting. So if we can reduce the power consumed by the memory devices, you can improve the power performance of your overall product significantly. As well, from the growing of the memory demand, we have server application. That's more or less the dominating factor in the past. We have PCs seeing a regain during the pandemic with all the home office workers. We have mobile devices, but what we do observe from the EDE vendor point of view is an increasing demand from consumer and automotive and industry. So we have the market demanding for more memories. That's as well reflected if you look into the market share of what kind of ICs are sold worldwide. Here are the figures from 2020. So that's significantly dominated by memories if we combine DRAM and flash. So that's the biggest fraction. As well, the amount or the percentage of low power DDR4 is growing. So that's public available data on how the different memory generations share market-wise these days. I personally do expect, as well from the experience from customer discussions and projects we do support, that low power DDR4 is taking close to 50%. That's my personal guessing. So it is quite likely that low power DDR4 can show up in one of your coming design projects. And just for those who are interested, who is making all these all these memories, a significant amount of memory devices is made by Samsung, close to 45-48%. These days, these are the figures from 2019. Then we have Hynix and Micron following on place 2 and place 3. So that's from the industry perspective. And we have this DDR memory evolution. On the left-hand side, we have the full voltage breeds DDR, DDR2, DDR3, DDR4. And we have an improvement in the I/O, bus clock, and in its transfer rate, and the bandwidth, which is possible using that kind of memories. And if we look onto the low power breeds depicted on the right-hand table, we see that if we look on low power DDR4, the performance, and even further if we look on low power DDR4X, which is the voltage scale down version, that's pretty close to the most sophisticated memories which are on the market these days, close to DDR5. So with a gain in the power efficiency, we have an incredible amount of bandwidth and memory performance. And that's quite interesting, and that's the motivation that many design engineers do use low power DDR4 memories in their designs, cross through all different industry levels. So I've supervised and supported customers using low power DDR3 from different industry segments in the last 2 years, from automotive, from industry application, even from consumer goods. So we see low power DDR4 as well on consumer electronic applications. What's probably overlooked, it is not just a scaled down version for the voltage of the regular memory. It's a standard on its own. So it's standardized by JEDEC. Low power DDR4 has been standardized by JEDEC already in 2014. It has different architecture, slightly different, slightly differing from DDR4 in the case of low power DDR4. We have, that's interesting, in the low power breeds of DDR memories, quite fast development cycle. So if we take into account that low power DDR5 is meanwhile standardized as well, we have 5 generations in 10 years now, while the, in quotes, regular DDR5 memory, DDR memory family has seen 5 generations in around about 20 years. We have the voltage lowered down. So therefore, we have the situation that was originally intended for mobile application because of this lower voltage demand. But meanwhile, as low power DDR4 is as well specified over wide temperature range, other industries have detected these memories and use them in a favored manner, like automotive. And we have, nevertheless, a situation that the overall umbrella standard DDR4 is defining more or less the cornerstones of the rules. So these documents do provide useful information. But however, there's a lot of additional information provided by the silicon vendors defining the specs, how to implement low power DDR4 using their devices. And that's supported throughout all the different silicon vendors, regardless whether it's Qualcomm or NXP, or here the examples from NXP and from Texas Instruments, or Xilinx, or Intel, stroke Altera. So you find the relevant documents defining you the guidelines to follow. One important thing to mention further is that contrary to DDR4, which has introduced pseudo-open drain technology for the signaling, we have now in low power DDR4 low voltage terminated logic, so low voltage swing terminated logic LVSTL, having the advantages in the power management. We don't have the fixed VREF voltage any longer. That's similar to DDR4. Another very important and interesting aspect from my personal point of view is that we don't have these fixed voltage thresholds any longer. Instead of that, the memory controller and the memory devices do negotiate during powering up the switching levels. So that's a kind of boot up sequence, and then the memory controller and the memory device know at what level a logical 1 or logical 0 will occur. But this means controlling the margins and controlling the timing is key for success. And therefore, as these thresholds are not clearly defined, just looking into one waveform is not sufficient any longer to guarantee and to validate significant behavior. So you have to look into eye diagrams in relation to the proper unit interval as a figure of merit. And we have these power management thing which is achieved by one additional bit, which is introduced already in DDR4 and as well known in low power DDR4. That's called data bus inversion, where bits can be flipped by turning these special bits to 1 and then on a per byte base, changing state from 1 to 0 again to reduce the power amount and to prevent symbol interference using a special coding that no information is lost. And that's very interesting and defining challenges for the further validation at the end. So what is the design problem? The design problem is that we have new features. Designers have to cope with transmission line losses. So therefore, low power DDR4 allows to put additional energy, a kind of boost on the signal, like shown in the picture on the upper right, to achieve at the receiver side, to achieve at the end a proper rectangular square, which does not exist, by the way. We have misshaped waveforms anyhow. But you can get additional energy. The question is this necessary? Because then you have an increasing power demand, and that's what we, by definition, try to avoid. So we have more stringent rules. Measurement is often challenging. So to measure on the small form factors, we have micro BGAs for the memory devices. We have crosstalk being more important. We have power distribution noise defining jitter and closing the eyes. That's undesired. We have the situation that in low power DDR4, the ICs can be tweaked, can be tuned in a very extensive way. So you have many different parameters you can change. Output driver strengths, these overshooting. You have embedded termination devices on driver and the receiver side. You can control the output resistance or the impedance. So you have many different things. And that's a kind of ZSL-like problem. So it is similar, complex, rather than implementing PCI Express on the board. You have to cope with losses, simultaneous switching noise. The technology tries to avoid these by this data bus inversion feature. And some IC vendors even define special measures, for instance, to cancel crosstalk effects or how wires should be designed. And you should have in mind that if you neglect all these requirements to a certain amount, then you will see scrap on the manufacturing floor. So then you have an increased yield, and that's nothing your management, your procurement really likes. We have a lot of reading material, so we have the different specs. We have the JEDEC spec for low power DDR4. We have supplement documents. All this can be collected, can be gathered from different sources, from JEDEC or from the IC vendors. The IC vendor pages do provide really information worth to collect and to read. Some of these information public available, some of these on request or by contacting the field application engineers. So it's highly recommended to use these. Here we find, and that's as well more challenging with the newer generations of DDR4, DDR, low power DDR, we find an increasing amount of so-called electrical rules. So we have the situation that modern CPUs can use different kind of memory interfaces. They can use DDR, DDR3 low power, DDR4, DDR4 low power. In this case, that's from an NXP IMX8. And these memory interfaces have to fulfill certain electrical rules like eye opening, like delay in terms of delay difference and not length difference. We have the crossing points of the differential pairs, which are used for the strobe and for the clock signals. So all these rules are pretty difficult to control, to check by just doing a visual board inspection. Instead of that, you have to have proper measures, a proper flow, and proper tools in place to check these dedicated electrical rules. So we have a very complex design problem. We don't have all the mechanisms which are probably known in PCI Express. They will come in future memory generations. So therefore, a careful pre-layout process, pre-layout studies, probably simulations to figure out what is the proper trace width, What is spacing to avoid crosstalk? What is the maximum allowed damping and delay by the bias in the interconnect path? Planning, technology definition is vital for the design process and for successful design. This allows as well to optimize structures cost-wise, form factor-wise, or to reach the maximum performance. So we have different steps which have to be addressed. Routing is more complicated as we have these tiny micro BGAs. We have more complex rules. We have breakout situations where we have different impedance levels from the memory controller to the receiving device. We have required trace width changes. We have very tiny trace widths. I recently did support a customer in a low power DDR4 project implementing 75 microns. So you have to discuss with your PCB manufacturer whether they can implement such technology. Material selection is paramount. Stack-up definition is paramount. The strategy for the neck down into the BGA or through connector fields must be done carefully. Wire transitions, the maximum allowed number of wires is typically constrained. Where to place them if you have a bus situation, to take into account that you have to have return pass wires. The return pass is of serious concern. Avoid under all circumstances any breaking of the return path. So not route over gaps, over cutouts. So plan your power distribution network accordingly. Target impedance is a new figure of interest, a new measure for the quality of the power distribution system. That's probably new for you as well. And skew is probably the most important thing to constrain and to implement skew compensation. Here, very likely you have to look into the length differences within the large BGA packages for the controller, for the CPU, for the FPGA. So if you have these length differences, they have to be taken into account in the skew compensation. Otherwise, you get signal offset and undesired signal behavior. Good high-speed design starts with good layer stack design and definition of technology. I think that's known. However, that's even more important in the case of low-power DDR4. We have quite an amount of different layer stack recommendations. Unfortunately, sometimes you have contradicting requirements from the memory vendor and the FPGA vendor. However, there are these minimum requirements, like Micron, for instance, is demanding it cannot be done with less than 6 layers. Okay, then probably you have to negotiate with your procurement. We need 6 or probably even more, 8, 10, 12 layers. Return pass considerations should be taken serious as well in the layer stack planning. So what are the layers for the return pass? What are the routing layers? Probably special routing layers for high-speed signals. Impedance requirements lower down. So I've seen impedance requirements going below 40 ohms for single-ended, below 80 ohms for differential. So you have completely different impedance windows like you may have had in the past. So you have to implement these different impedance rules, these stack-up rules, in the CR-8000 process, and then probably using what-if capabilities to optimize these structures to come for all the different required signal cut sections to proper impedance situations. So CR-8000 allows then to create proper rule width stacks coping with all these different impedance situations, cut sections, whether you have to implement it structures as a microstrip or as an embedded strip line or coupled strip line. So that's available in the technology definition already in the front end. Then you have to cope with different placement rules to ensure proper delay matching. So we have here the situation in this document from Texas Instruments, a minimum and maximum difference of the placement coordinates of the of the CPU and the memory device to ensure delay matching. And then the implementation here, we have one memory device here on the real board. We have two memory devices, as well requirements on copper pouring for the return pass underneath the memory controller and underneath the memory itself. Here, the design guide, here's implementation on the board. We have these electrical requirements, and I did mention skew, and these skew figures are tiny these days. So we have numbers narrowing down to below 1 picosecond. So here from a guideline from Texas Instruments, within a differential pair, the skew within the differential pair should not exceed 0.4 picoseconds. That's pretty tiny. Even the 2 picoseconds between the different signals of one signal class, 2 picoseconds means a third of a millimeter, depending whether you implement strip line or microstrip because of the different velocity. Assuming standard FR4 material. So we have tight electrical rules. So here then you have to consider, of course, different lengths within the IC packages or the wire lengths, because they do matter if we are talking on skew requirements of a fraction of a millimeter. We have topology requirements, which in theory can be rather simple because the times of these balanced H trees, which probably some of you may remember from the times of DDR2, they are gone. So we have recommended daisy chain. Okay, nice. Rather simple. Even further, if we have just one memory device, we have a point-to-point connection. Sounds easy. Unfortunately, due to these timing skew requirements, the silicon vendor make even a simple topology complicated, as they define special rules for special regions of these topologies. So we have these breakout regions having dedicated impedance requirements. This typically cannot be covered using the rules by area feature all CAD systems know since many years. That's running out of steam. You have to have proper constraining and checking mechanism to cope with the breakout rule situation where the silicon vendor name the transmission line structures accordingly. So here we have a segment L0 having a requirement 50 ohm plus minus 10%, and then L1 is narrowing down to below 40 ohms plus minus 10%, and then we have another section narrowing up again or moving up then up to 52 ohms. This is the case for single-ended structures. This is the case as well for differential structures, and this must be covered. And that's a rather recent document from Xilinx from February 2021 from one of the modern FPGAs. But that's covered in the constraining features of CR-8000 already in the front end. So the topology template feature, which you can launch from the constraint browser, allows what we call smart constraining, where you can implement these situations with the changed impedance structure, and you can give these segments as well minimum maximum lengths, and then can design accordingly these rules. So you can create proper topology templates, and then you assign these templates within the constraint browser to nets, to groups of nets, to net classes using the topology tab. This then creates in a dialog a mapping between the nodes in the topology and the nodes in the template. And by just 2 mouse clicks, then you have assigned all the rules which you have defined on the topology template base, mapped automatically by inheritance to all the nets where this topology is assigned to. So that's smart constraining, fast constraining by inheritance. So then you don't have to constrain all the nets one after another. You can define the generic template and then constrain them in a one-shot operation. The constraint browser allows as well smart checking whether constraints are met or violated. So here an impedance review of the selected low power DDR4 interfaces, all the different signals in charge, where we have here the check for the single-ended impedance on a detailed manner, on a per segment base. And we see here for the different segments, which are identified here by the reference designators, the different impedance values. For differential structures, we have as well here the differential impedance listed. Violations are marked in red. So you can easily validate whether your relevant constraints are met or probably you have a violation and have to change some structures. You can even on a more higher level use a constraint browser to verify whether your impedance target fits into the window which you have defined. Here we have a rule, 45 ohms plus minus 10%. That's matching into an impedance window between 41 ohms and 49 ohms. And here we have a matching of 100%. So all the constraints are here fulfilled. Other electric constraints may contain things like the maximum delay from the memory controller to the memory device at the end. Here we have a point-to-point case because in this situation we only have one memory device, and the rule states 200 picoseconds maximum delay, including the package. Allowed in the constraint browser, it's reported that we have 120. So we are okay compared to that rule for the selected design here. You can go even a step further if you would like to dive into the details. You can use a simulator, the embedded signativity tool, which is part of CR-8000, to validate the skew within a group of nets, for instance. So here, for example, I have all the column address signals and the maximum skew between the shortest and the longest. And here the skew requirement is fulfilled too. You can check this either in the constraint browser, or if you would like to look into the details as well, like what is the impact of the package. So we do report the die and the package waveform. You can use a simulator on a single mouse click, and that's the key, on a single mouse click from within the constraint browser or from within the SignForce. For signativity, there are further aspects gaining importance. I did mention that eye diagrams are the favorite figures of merit to check the validity of signals. However, you should as well look not only in time domain, but as well in frequency domain, because losses, so insertion loss, return loss, are gaining importance. Then we have the situation that you can change the device behavior by setting some registers and changing driver strengths and changing on-die termination. So all these different features, which are meant to optimize signativity, require either that you build up a prototype and then do a kind of optimization cycle, or using any kind of virtual prototyping to allow these parametric studies. What's often investigated is the waveforms, whether the receiver signals are monotonic, either for one single signals or for a group of signals. Here, the red waveform is the driver side, in this case the IMX8, as well as the column address signals. And the green waveforms are the voltages at the memory device, at the micron. They do operate, they switch monotonic. We have eye diagram results on the driver side, on the receiver side, showing the indication that the eye is open enough and behaving properly, so no additional measures seem to be necessary here. And if we look into the switching time of the involved devices, we may be rather surprised. So for supporting signativity processes, which are in place on many customers implementing a high-speed design process, so to a certain extent they use signativity simulations, and signativity simulations use IBIS models provided by the IC vendors. And the IBIS models do reveal the switching times. And here, on the receiver side, ISSI is the second source in this case. We have switching behavior of the memories below 60 picoseconds. So that's fast. So we are talking here on ultra fast silicon devices. That's what you have to take into account. And the features of low power DDR4 unfortunately open a little bit the box of Pandora, if you would like to phrase it that way. All the different settings you can define on driver side and on the receiver side are reflecting different models in the IBIS model of the silicon vendor. So here we have an excerpt of the IBIS model list of the IMX8 from NXP, offering or supporting different memory interfaces. And for the low power DDR4, we have a couple of different models available which do reflect the different settings, different output impedance, 40 ohms, 48, 60, 80, on die terminations with different values, preemphasis on off. So at the end, and that's the message behind that slide, you have to closely communicate between your hardware designer and probably as well the people which create the software and make the board working at the end. Not to compare apples with pears, but to simulate the proper setting, which gets into the real operation at the end. But that's supported by the software. These different models on driver and receiver side show a complete different behavior. So here we see this tiny little overshooting, and we see different voltage waveforms. I don't want to dive into the details of the different waveforms. Just takes a message. The different models and different settings behave differently. So to choose the proper setting can be key for success in a low power DDR4 design. Very often underestimated is, meanwhile, in modern DDR memories, the importance of power integrity and the behavior and the aspects of the power distribution system, because power distribution noise creates jitter, creates disturbing factors which will close the eyes. And we have a more complex voltage scheme. If we have an IMX8, this processor knows 8 to 10 different voltage rail. For the termination, we don't have the external VREF any longer, so therefore proper termination voltages are key. We have tight form factors and we have fragmented power islands, power structures, so they are very likely irregular. So therefore, we will see narrow areas, narrow traces where we have a high DC resistance. So we have situations called IR drop. So we have a decrease of the voltage by a higher current caused by a higher DC resistance. And we have resonance situations of the impedance. All that is not desired. And we have requirements from the standards or from the IC vendors on the allowed tolerances. Like for low power DDR4, we have a plus minus ripple voltage allowed of 60 millivolt. That's not much. We have quite an amount of power consumed by the different power rails for typical design. That's an example from a design project. And we have different questions which then may occur pretty late in the process, like, do I need probably additional wires over here because of all the currents? What about the decoupling capacitors? Are the 5, to say a number, enough, or do I need some additional ones? Probably I have to reshape this copper array here to cope with some resonance or to cope with some IR drop. What is the current over here? So all these are questions then typically yielding to reiteration cycles, and these are all power integrity related questions. To address this, we have embedded within the CR-8000 design force tool the embedded power integrity simulator, which can cope with DC aspects, so simulation steady state and investigating in IR drop issues, current distribution or DC voltage distribution, current flow to compute what is the maximum amount of current any of the power wires is exposed. You can compare these current figures against current limits, which you can define within the tool. You can do different amounts of what-if studies within the PI tool without the necessity to change layout parameters to the deepest extent. We have as well AC simulation capabilities within the PI simulator, which is allowing to check the target impedance, which is given by the IC vendors, which is typically not constant over frequency. So this target impedance changes typically over frequency from 100 kilohertz to 1 megahertz. Probably I have a value X, then from 1 megahertz to 100 kilohertz, I have a value Y, and then from 100 megahertz to 2 gigahertz, I have a value Z. So you can use in a very straightforward manner fast. So these simulations typically take less than 2 to 3 minutes, depending on complexity of the power distribution network. You can validate the behavior. Here we see the behavior of the AMX8 on the left-hand side, looking pretty good. We see as well the behavior of the Micron device looking good too. And on the upper right, we have a special diagram as well generated by the PI simulator. That's the behavior of the decoupling capacitor group, because we have more than one, of course, looked one after another, and as well in the red waveform, the parallel circuit of all the decoupling capacitors and how they act in frequency, and that's pretty good too. This brings me to the conclusion of my presentation, where I have to say that discussing with users in our customer base, I see DDR4 and low power DDR4 becoming a commodity. So they are showing up more and more on a daily basis in different industry applications. So I've seen projects in automotive, I've seen projects where customers are doing mobile devices, I've seen projects in industry automation, even in consumer electronics, I've seen low power DDR4 projects. So this technology defines new challenges. That's not just slightly, it's significantly different to previous technologies you may have implemented. We have lowered margins. We have a lot of electrical constraints and requirements, which are difficult to check just by design rule checks. So we have these crossing points for differential pairs. We have real electrical skew, where you have to include the packages and the wires, the length of the wires. This typically should be done before the first prototype is ordered. We have new design methodologies, which people are probably familiar from PCI Express, but not from memory interface design. That's supported by CR-8000, so we have the high-speed design process in place. So we have comprehensive support for constraining and concurrent analysis featuring signal integrity and power integrity to allow you to implement low power design successfully. Pretty important is collect all the requirements. So I know customers then creating own documents and feeding these documents then into the constraining process. Starts the constraining in the design gateway. So during the schematic, it's never too early to start rule definitions constraining. Defines the technology pretty carefully. So technology definition includes stackup definition, material definition, impedances, review during the process, and perform pre-layout studies. That's highly advised. Take into account that you have tiny details which can have serious impacts. Route carefully against these constraints. The automatic features like automatic lengthening and auto routing can help verify the results concurrently. You have pretty brutal timing and skew requirements. You have slew rate requirements. You have buffer margins. So all these items make the picture rather complicated. To give you some tips and tricks, there are some issues which should be implemented, some routing recommendations like what is the proper order according to the different byte lanes if you have more than one memory chip. Take into account proper spacings, then you have to route into the BGAs, do a proper planning of the wires, because if you have differential pairs, you must route the two legs of the differential pair through the wire field. Otherwise, you make a general design rule mistake if you spread the differential pairs apart. Keep in mind that you have to fulfill and implement these topologies, and CR-8000 is supporting on different levels, either on a per design base at component level using the pin length attribute, or there's a special attribute for creating a package. If you use that device quite often, then you can use the wire length in package attribute on the package level to support the different package lengths to allow skew matching. So that's supported in the process. And at the end, to give you an outlook in the future, DDR5 is ratified. Low power DDR5 is ratified too. There's graphics DDR, which is a special breed, more or less sharing the name. So the next memory generation is knocking to the door. I already have had discussions with customers considering those. That's typically implying different memory architecture. So as we have multiple dies comprising the overall memory module, we have either package on package, or we have a thing called a memory cube, where we have up to 4 dies or even more, as shown by the picture from Micron, stacked into one device. So this now involves even more complicated signaling schemes. So we have technologies with equalization on the driver side. That's already known in low power DDR4. But we have as well signal recovery on the receiver side, as we probably may know from ZDA's technology. So we have things like FFE, DFE, CTLE. So more possibilities, more features, which unfortunately define more challenges in the design process. If you have a memory DIMM for DDR5, you have a special power management IC on the DIMM, which is converting the voltage for the memory devices. So we have tougher power integrity challenges on the board. And we have bit error rates being a new challenge, which you probably have not been involved with so far. And that was what I had in mind to present on with respect to the low power DDR4 memory design challenge. Thank you very much. I hope you enjoyed the presentation. Thank you. And I'm looking forward to meeting you sometime in person and meeting you again. Bye-bye.